Hello. Welcome to the first trimester extra credit 1 essay question. So the basic prompt for this question is Cotton Eye Joe reacts acetic acid, which has the formula CH3COOH, with a molar mass of 60.052 atomic mass units, with calcium hydroxide, CaOH2, molar mass of 74.093 atomic mass units in the following reaction. Acetic acid plus calcium hydroxide becomes CaCH3COO2 plus H2O. H2O will be in the liquid state. Everything else will be aqueous. So the first step will be to write the balanced molecular equation for this reaction. So you would see just by counting everything from the reaction that you would have on the reactant side, you have 2 carbons, 6 hydrogens. Here's 3, 4, 5, and then times 2 is 6. You would have 4 oxygens, 1, 2, then 1 times 2 is 4, and 1 calcium here bonded to the hydroxide. And then on the reactant side, you would have, this time you'd have 4 carbons because you have the acetic acid, but now you have 2 of them with the subscript of 2. Because of that, also the hydrogens, now you have 6 here. It's 3 times 2 plus the 2. Sorry. You would have 8 here, I believe. Yeah, right. 6 times 2 plus 2. So that's 8. And then the oxygen, over here you would have 5. 1, 2 times 2 is 4. Plus 1 is 5. And then you still have the 1 calcium. So you would start this by balancing. Well, the most obvious thing to balance would be the acetic acid, because that is the only thing in the reactant side that has carbon. So you would add a 2 in as the coefficient of the acetic acid. So now I have 4 carbons. On my reactant side, I have 6, 8, 12 hydrogens. And, is that right? 6, 8, yep. No, sorry, 10. My apologies, 10 hydrogens. And, this is 4, I believe, 6 oxygens. So now I'm looking at this and I see, okay, the main way I would increase my oxygen by 1, because that's the easiest thing to do here, would be adding 1 more oxygen. The way I would do that is by increasing the coefficient of the H2O, because just adding a 2 in front of that, that's going to add you 1 more oxygen. So now I have 6 oxygens, and with that I have 4 hydrogens, plus 6 here is 10. So now my molecular equation is balanced, and you don't need a coefficient for these two. The next step would be for this acid-base reaction, which you could figure out that it is acid-base by looking at the reaction process. You would now you want to create the balanced net ionic equation. So you'd first start by just creating the basic ionic equation without canceling out the spectator ions. So you'd break up all ionic compounds into their component ions. So you have Ca2 plus 2 OH minus plus 2 acetic acid. And then on the product side, you would also have the Ca2 plus 2 CH3COO minus. It's not explicitly stated that it has a -1 charge, but you can figure it out because this is an acid-base reaction. Since it's donating one of its protons, which has a positive charge, now that it's losing the positive charge, it goes from neutral, no charge, to -1, and you have the 2 H2Os. So you would start here. The main thing you would do is cancel out any spectator ions, which is something that would be on both the reactant side and the product side. The one thing we have of that here is the calcium, so cancel out the calcium. And then since everything else has a coefficient of 2, you would just get rid of the 2. So here it's just OH minus plus CH3COOH becomes CH3COO minus plus H2O without any of the coefficients. The next step is identifying the acid, the base, the conjugate acid, and the conjugate base in the ionic reaction. So your acid would be the acetic acid. It's in the name. That would be the acid, but you'd have to explain that's because it donates an H plus proton to the OH minus when it becomes H2O. So that makes OH minus the base. Therefore, H2O is the conjugate acid because it has just accepted the proton from the acetic acid. And the weird handwriting, CH3COO minus would be the conjugate base since it's now donated a proton. And because it's now donated a proton, it is now in the position to accept a proton. So the next step, step D, draw the electron dot Lewis structure of acetic acid. This is just, so you can understand the properties of these substances. So this is what the Lewis structure would look like. You have the C bonded to 3 hydrogens over here. Then it is bonded to the other carbon. This carbon would have a double bond with one of the oxygens. And then it is also bonded to the other oxygen, which is bonded to hydrogen. This, you need the oxygen bonded to hydrogen in order to create the hydroxide group. And this, layout of everything with the double bonds is the only way you can make sure every, atom here has a formal charge of 0, since obviously the charge of the overall acetic acid is 0. The next step is to identify the intermolecular forces in acetic acid, and then use it and justify, would this have a high boiling point or a low boiling point? So, acetic acid contains London dispersion forces and hydrogen bonds. This would result in a high boiling point because hydrogen bonds require a great amount of energy to break, and the London dispersion forces would be relatively strong compared to a molecule like water, H2O. H2O also contains hydrogen bonds because you have the 2 hydrogens bonded to water. But because acetic acid is so much of a larger molecule compared to water, it will have a much higher boiling point. And water, in and of itself, would be considered a high boiling point molecule. Especially if you compare it to a lot of other molecules out there, 100 degrees Celsius is a lot. So then in part F, we are introducing some stoichiometry. So this is assuming the acetic acid is present in 50 milliliters of a 0.3 molar solution, and the calcium hydroxide exists in 400 milliliters of a 1.2 molar solution. So the first step would be to calculate how many moles are present using the formula to find molarity, which is moles of solute over liters of solvent equals molar. So this is what it'd be like for acetic acid. Multiply the 0.3 molar by the 0.05 liters, converting 2 liters, of course, and you get 0.015 moles of acetic acid. And then over here, multiplying the 1.2 by the 0.4, you would get 0.48 moles of calcium hydroxide. Then step G, that was more molarity. This is more proper stoichiometry. Now you're going to be asked to convert the number of moles of acetic acid and of calcium hydroxide into CaCH3COO2, which is obviously our product. So, and in addition to this, you have to identify which reagent would be the limiting and which would be in excess. So the first step would be converting your acetic acid. It doesn't matter what step. I did the calcium hydroxide first. You would basically use the mole ratios that we saw here in the balanced reaction. So in the balanced reaction, we have 1 mole of calcium hydroxide, 1 mole of CaCH3COO2. And so we're just going to stick with 0.48 moles of your product. And then similar story for the acetic acid, except this time because there's 2 moles of acetic acid for every 1 mole of your product. You're going to have to divide by 2, so there will be 0.0075 moles of CaCH3COO2. Because of this, the acetic acid is the limiting reagent, because you're only going to be able to react those 0.0075 moles before you run out and you can't react anymore, so the calcium hydroxide will be left in excess. The next step is calculating how many grams in excess you have of that calcium hydroxide after the reaction. So the first step would be, first, how many moles of the CaCH3COO2 do you have after you run out of acetic acid to react? So you do 0.48 moles minus 0.0075 moles. That gives you 0.4725 moles of CaCH3COO2. And then you would multiply that by the mole ratio, which is 1/1. And then you would multiply that by the molar mass of calcium hydroxide, which was given to you in the initial prompt. And you would find you have 35.01 grams of calcium hydroxide remaining in excess. And finally, there are going to be 2 problems involving titration. So here, Cotton Eye Joe titrates the 50 milliliter solution of the 0.03 molar CaCH3COO2 using 0.5 molar sodium hydroxide. So he's performing a titration, and he creates this titration curve. The way he does the titration is he pours the CaCH3COO2 into a volumetric flask. Then he adds 2 milliliters of distilled water to dilute the concentration, fills his burette with sodium hydroxide after rinsing it with distilled water, and then he will drop the sodium hydroxide into the solution until he reaches an equivalence point, which you would know by a visual indicator like a color change. So here, let's just draw an X where Cotton Eye Joe would have noticed that the acid and base have reached equivalent concentration. As you can see, it is right here, right around 20 milliliters. You can see, once you reach 20 milliliters of your sodium hydroxide, the acid and base will be at equilibrium, and now the more and more of the sodium hydroxide you add, which is your indicator base, then you will it's going to become more and more basic. You can see because CaCH3COO2 is a weak acid. It is a weak acid, so the pH here is going to be starting a little higher, but that's not really important to the prompt. The X draws here where the graph starts to shoot up. And then this is the final part. So Cotton Eye Joe knows that this titration curve may not be perfectly accurate, so he is going to perform multiple rounds of the experiment. When he performs the titration again to confirm his results, he notices that in the second trial, he needed to add a lot more sodium hydroxide before he reached the equivalence point. So the final question is just, what could have caused this error? Why does he now need to add more sodium hydroxide? So he needs to add more of the base because the solution was more acidic than it was in the first trial. This likely means that he added too little distilled water to the solution, less than the 2 milliliters that he used in the experiment, like procedure, and in the first trial. Because the solution had a higher concentration of the acid, a greater amount of the base would be needed to added in order to balance the solution and reach the equivalence point. So his error is that he added less distilled water, so the solution was less diluted than it was in the trial run, which is why there's this discrepancy between the two. And thank you. Thank you.